Hello, everyone. This is Mr. Ihsan, and I shall be glad to guide you through this question posted on our Reddit subgroup, A-Levels. It seems to be a mechanics problem, basically on elastic forces. So here what I have is I have two blocks, A and B, and each masses of 0.8 and 1.2 kilograms. And yep, they're stuck together, and I have a spring. That's actually a spring. The original length, natural length, is 0.5 meters, and modulus of elasticity is 49 meters. So that's an interesting point here. I'll come back to that. Modulus of elasticity with the units 49 newtons. Now, at the end of the spring is attached to the top of the block A, and the other end is spring is attached to point O, as shown here. Okay, fine, fair enough. And the first part of the question says that the system is in equilibrium, so there's no net force, there's no motion, it's balanced, and I need to find the extension. Okay, good. So let me start with this interesting concept of modulus of elasticity, just to explain it and basically, solve the problem. So now, I don't know what spec this comes from, but normally when we speak of modulus of elasticity, the units for that, okay, for modulus of elasticity is newtons per meter squared. All right, okay. Now, so if you use the modulus of elasticity, which is this, newtons per meter squared, or Young's modulus, then you can find the spring constant from this equation, which is basically E times the cross-sectional area of a wire or whatever you have over the original length. Okay, that's how you work out K from modulus of elasticity. Now, the problem here is I have a spring. I don't have a wire or just a shape. I have a spring, which is coiled. So here I have a modulus of elasticity is given in newtons. So really what this tells me, let me just highlight this. This modulus of elasticity really is that value altogether. And if you multiply that out, it gives you newtons. So I'll call that E star. Okay. So basically how to find K? K is basically E star, which is this modulus in newtons of the spring divided by the original length. Very good. Okay. So now, how can I find now the spring constant from those two values? Well, I have those values here. I have that 49 for this E star value over the original length, which is 0.5. And if I do my maths correctly, I have 49 divided by 0.5. If you do that, you multiply simply by 2, which should give me 98 newtons per meter. So this is my spring constant. Okay. All right. Good. So now I can apply Hooke's law. If you remember, Hooke's law says that the force applied on a spring equals the spring constant times the extension. Now I need to find my extension for this problem for part A. So therefore, the extension is simply the force applied over the spring constant. Now, what is the force applied here? Well, it's basically the total mass times G, right? So here I have 0.8 plus 1.2, which is the total mass. Times 9.81 if you wish, or 9.8 is just because this is 98, this will help, over 98, okay? Now, if you do all the maths and the number crunching correctly, we should get an extension of 0.2 meters, and that's the first part, okay? Now, for the second part, if I look here at the second part here, it says, shows that elastic potential energy of the spring when it is in equilibrium is 1.96 joules. Now, just to remind ourselves, if you remember, the equation for the elastic potential energy is simply half kx squared, or if you wish, if you lost half of the force times x. Okay. Now, of course, you can use either of them. I'll use that format. Okay. If you remember, we had from the previous question K to be 98 meters per meter, and our X was 0.2. So we simply substitute and see if we get 1.96 or not. So elastic potential energy should be equal to half times our K, which is 98, times our X extension, 0.2 squared. So let me do the mathematics for that. Okay, 98 times 0.5, and surprise, surprise, P elastic potential energy is 1.96 joules. So nailed it. Yeah, that's the second part. Now we come to the part C, which is a really interesting one. And basically, it asks us to show that if mass B falls off and basically mass A jumps up on the spring and reaches a point, it will basically give me that expression. Now, let me just translate everything here. Now, it says that the final state here I have the top wall with point O, and here I have a spring, and here I have the final length now, okay? Now, let me just put some, here is the equilibrium point with no extension. I'll call that equilibrium. And here is the original starting point here, okay? And here I have with mass A, okay? All right. Now, if you remember from the previous parts that this extension from here to here is 0.2 meters, all right? And now this extension from the equilibrium point to that is x. And now it's compressed. It says here that the spring is compressed by x meters. So how can we show that? Well, we show that by equating energy balances, okay? We started off from this position, all right? And let me start off with elastic potential energy in the spring as 1.96. That's from part B, joules. That's elastic potential, right? Sorry, that's elastic potential energy. And then what happened is that we jumped up all the way to that new height. So the distance traveled from this position, the original one, at 1.96, the new one, okay, we traveled a total distance of 0.2 plus x. So that part of the energy is transferred to gravitational potential energy. And if you remember gravitational potential energy, so EG is simply the mass G and the height or delta H traveled, right? Okay, so really what happened here is that I took from the balance of the original balance of 1.96 joules, and I took some of that to convert to potential energy. And therefore, the final balance, okay, of elastic potential energy here, the final balance is simply the compression here, that x, half a kx squared, okay? So that's x. Half, that's potential energy, the final one, okay? All right. Okay, so I'm going to put that balance of energies in an equation, all right? So let me put that one here. I'll start with the initial balance, which is 1.96 joules. And I took from that, okay, basically the mass, I'll put mass G, and the H, which is x plus 0.2. And all of that should equal to be the final balance of energy, which is half k x squared. All right, great. Now what we need to do is just do some substitute values and do some number crunching. So let's do that, okay? All right. Let's start with the following, okay? First of all, I need to put the values here, the numbers for that one. So let me put that 1.96. I'll put the numbers and then expand, okay? So if I multiply mass, which is 0.8, times 9.8, which is the gravity constant, I should get 7.84, okay? And if I expand that here, 7.84, I get the following, okay? Now minus, 7.84 x, okay? And minus 0.784 times 0.2 should give me, if I'm not mistaken, should give me a 1.568. 568 equals, of course, k is 98, so 98 over 2 x squared. Now let's multiply everything by 2, okay? So I'm multiplying every term by 2. And of course, just to get rid of the 2. And if I do that, just getting you through the steps of the number crunching, 1.96, if I multiply that by 2, I should get 3.92 minus I'll put the numbers together. So 1.568 times 2 gives me 3.136. Just to not to help you, not to track what's happening. This is the same value as this. Okay, and yeah, let's continue. And so I'm left with the term, the x term, which is 15.68 x equals 98x squared. Okay, now let me write this. I need to clear this up. Okay, so I'm going to continue. I'm going to erase now. I'm going to continue up. So please just a minute. I'm going to clear up and rewrite this neatly. Now this is what we have left with, and therefore let's just simplify that. If we simplify that mathematically, no, hang on, I got 98. Okay, let me divide everything by 98. Okay, so I'll do that. Divide by 98, divide by 98, divide by 98, and divide that by 98. If I do each term divide by 98, I should get the following. I should get 0.004. That's minus 0.032. Okay, minus 0.16x equals x squared. Great, excellent. Now, good. If I now look at those two values, they simplify to 0.008. Okay, of course, this is the same, minus 0.16x equals x squared. Now, let me bring everything to the right-hand side. And of course, then I'll have the following. I'll have 0 equals x squared plus 0.16x minus 0.008. And that's it. That's indeed the equation for part 1 in C. Good. Now, really, for the second part, I just use Solver to solve this quadratic. Of course, I'm sure you all know how to solve your quadratic problems. And if I do that, I should get two values, x1 to be a negative value, 0.2 meters, and the second root is 0.004 meters. Now, before I end off, let me ask you a question. Which one would be the answer? Now, let me just come back to the main point. It's compressed, so I should have a negative value. So really, we should pay attention to the meanings of those values. Of course, I have equal values, but that one with the compression is the one I'm looking for. So that one here is my answer. All right, I hope that has been beneficial. All the best to you. And by all means, keep posting those questions and I'll be happy to answer. Bye-bye.